Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is hydraulics math. Our objective is to review the basic mathematics skills and properties we'll be using in the hydraulics and electrical control of hydraulics playlist. Additionally, this lecture will preview basic hydraulic concepts using unit derivation exercises. First and foremost, you need to come to the unconditional realization that this is not a math class. This is an applied mathematics class about hydraulics. This playlist discusses hydraulic properties using numbers and mathematics skills, which I expect you to already know and feel comfortable applying with no outside guidance. The intended purpose of this playlist is hydraulics, not math. This being said, I'd like to perform a brief review of common formulas, units, and mathematics skills we'll be using during the course of this series. To immeasurably enhance your interest and active participation in this exercise, you'll be happy to know that it doesn't get much harder than this. This being said, this lecture is pretty long, and you might have to break it up into a couple different sessions. Hydraulics, in contrast to electronics, uses the same handful of formulas over and over at the level we intend to discuss it. If you learn to effectively and efficiently use these formulas and perform these calculations and unit conversions today, you will never have to learn these steps again. The same methodology employed today will be employed the next day and the next day and the next day. Take this lecture seriously and get involved in the calculations. Pause the lecture when asked to do so and take your best shot at the illustrated example problems. Ideally, your answer should match that of the illustrated example problem. If not, the illustrated example problem is there to lead you to the correct results. Additionally, the calculations we performed today largely demonstrate important basic hydraulic properties we'll revisit in later lectures. Learn the math behind the theory today and get the math off your back. With this lecture on a leash, the rest of the hydraulics and electrical control of hydraulic systems playlist should be easier than finding a baguette in a French person's bike basket. A couple housekeeping rules before we begin. This lecture is meant to be an addendum to the DC Math, Engineering Notation and Prefixes, and Unit Conversion lectures available at the Big Bad Tech channel. If you haven't watched these lectures yet or only dimly recall their contents, I'm asking you to do so now. The contents of this lecture operate under the presumption you can perform the following tasks. Use the order of operations for manual calculations. Algebraically manipulate an equation to solve for an unknown value. Set up your scientific calculator such that it displays numbers in a usable format. If you're using a TI-89 Titanium Edition graphing scientific calculator, my recommendation is to set it up in the following fashion. Display digits float. Exponential format engineering. Exact approximate. You should be able to use the order of operations on a scientific calculator, use efficient and effective calculation tactics, and properly round a numerical result, express a number using SI metric units using proper engineering notation and prefixes, convert between units employing different engineering prefixes, and convert between unit systems. If at any time you feel incapable or unqualified to use these tools, I am urging you to visit the aforementioned lectures and get confident in these skills. The behavior of a hydraulic system is dependent upon numerically quantifiable properties, and one must be able to interpret observations numerically. Mathematics is the language of numbers, and you must have a basic fluency in this language to understand and interpret the properties you observe. If you don't have math, go get yourself a big grocery bag of math and eat out of it every single day until you're full of math. Math is cheap and plentiful. There are a number of freely available resources that teach math, principally Khan Academy. There are more math videos at Khan Academy than there are infinitely small points in an infinitely long line, and this single lecture is a feeble attempt at packing a bunch of math goodies in a lunch bag and shoving it in your hand before I push you out the door. As big as a deal as I'm making about this, don't stress about this. Yes, math is necessary, and without it, hydraulics will be absolute nonsense. But math is not impossible. Math follows rules, and the rules never change. Just obey the rules, and you'll be fine. Before we begin our discussion of hydraulics math, let me issue this warning up front. Expect inaccuracy in both calculations and observations. The two major sources of inaccuracy in hydraulics are practicality and interpretation. Firstly, The principal linear actuator employed in hydraulic systems, the hydraulic cylinder, is, as the name implies, cylindrical in shape. Since the calculation of circular areas and cylindrical volumes involve the transcendental number pi, any approximation of pi less than infinite decimal places will be slightly inaccurate. Since it is often impractical to perform calculations using pi carried out to infinite decimal places, we'll settle for a reasonable degree of accuracy. Secondly, sometimes instrumentation employed in hydraulics, such as pressure gauges and flow meters, are analog, not digital in nature, meaning a needle meter that points at numbers on a scale open to interpretation. Don't blow a hose if your calculations call for an observed pressure of 487.3 psi, and your pressure gauge's needle is pointing to the general vicinity of 480 psi. You're in the right neighborhood. If this needle is pointing at 48 psi or 4,800 psi, you're not only not in the right neighborhood, you're in a bad neighborhood wearing the wrong shade of red and about to get jacked. Additionally, don't be surprised when observations capable of interpretation discrepancies employed in calculations yield slightly inaccurate values. Your results, although subject to interpretation errors, should be in accordance with theory. Don't stress out if your observations are off by a minute amount. Do stress out if your observations are wildly disproportionate or not in accordance with theory. Let me remind you, I am a man of action, and trivial squabbles over errors of 0.00 nothing are far below me. Call this conduct unbecoming of an engineer, or call it efficient and effective engineering education. What I care about is the basic concepts of hydraulics. If you divide when a concept clearly indicates you're supposed to multiply, you are wrong, and no amount of polishing will make this fact shine. If your answer is off by 0.00 nothing, you're right. Don't stress about trivial things. This being said, here are two best practices to use when performing calculations. 1. The previous results key on your calculator makes it very easy to obtain accurate results during the course of a multi-step calculation. 2. Use the complete previous results during the course of calculations and only round the final result to the desired decimal place. This advice is immeasurably useful when performing multi-step calculations, as we will in a moment. This saves you the drudgery of re-entering long strings of numbers, reduces the chance of transcription errors, and prevents the accumulation of rounding errors. Last but not least, think visually. Draw pictures. Make sure these pictures accompany your notes and formulas. Think about shapes. Think two-dimensionally. Think three-dimensionally. Squares are different than circles. Cylinders are different than tubes. And circles are different than circles with circular holes cut out of the center. If you can visualize these differences, a lot of hydraulic properties will be self-evident. These blanket warnings and best practices having been issued, we are now ready to discuss hydraulics math. We'll discuss common hydraulic units, algebraic manipulation at the unit level, unit conversion. We'll learn to calculate circular and annular surface area, and cylindrical and tubular volumes. We'll discuss flow rate and time, displacement, and finally, pressure and force. As I mentioned previously in the unit conversion lecture, available at the Big Bad Tech channel, I am normally an ardent supporter of the SI metric system employing engineering prefixes simply because of its intuitive ease of use. My dirty little secret is my use of US customary units when discussing hydraulics. This is for two reasons. One, I learned hydraulics way back in 9th grade, deep in the cultural dark ages of the late 1980s, kind of when the mullet was at its peak. And with this level of historical inertia, I regrettably resort to what I'm most comfortable with. Two, far more important than my perceived familiarity, is the fact that the US customary units blatantly and explicitly tell you what the unit is intending to measure. A liter, a metric unit of volume, doesn't really hint at how one directly calculates volume, whereas the volume expressed in units of cubic inches directly tells you that there is a length in inches, times a width in inches, times a height in inches, as in a cube of a certain volume expressed in cubic inches. Another example might be pressure. Pressure is expressed in the U.S. customary units as pounds force per square inch, written as PSI. The unit PSI expressly tells you that this is the amount of force, measured in pounds force, distributed over a given area, measured in square inches. The SI metric equivalent unit of pressure, the Pascal, not only gives no direct hint to its calculation, it's also a rinky-dink little pipsqueak of a unit, taking a ridiculously large quantity of pascals, approximately 6,894.8 of them, to equal a single psi. It is for this reason the units of Pascal are often packaged into more usable quantities of kilopascals, where 1 kilopascal is equivalent to 1 times 10 to the third, or 1,000 pascals. It is for these reasons I regularly use U.S. customary units when first teaching hydraulics. Students can often directly derive properties from the concepts expressly implied by the units. Algebraic manipulation on the unit level is very easy. If pressure is defined as units of PSI, or pounds force per square inch, or more generally, force per unit area, a simple rearrangement of these concepts tells us that force is units of pressure times units of area. Larger pressure, same area, means more force. Smaller pressure, same area, means less force. Same pressure, more area, means more force. Same pressure, smaller area, means less force. Another equally valid rearrangement of these units tells us that area is units of force divided by units of pressure. This three-variable relationship is known as Pascal's law, and it is the principle that governs the force exerted by a hydraulic actuator. What about flow rate? A unit of flow rate expressed in U.S. customary units is the gallon per minute, expressed as GPM. This explicitly tells us that flow rate is a given volume of something expressed in units of gallons, entering or leaving space over a period of time in units of minutes. Flow rate is volume per unit time. A rearrangement of these same concepts tell us that volume is the unit of flow rate times the units of time. Larger flow rate over the same time means more volume. A smaller flow rate over the same time means less volume. Same flow rate for a long time means more volume. Same flow rate over a short span of time means less volume. It makes sense. Another equally valid rearrangement of these concepts tells us that time is units of volume divided by units of flow. This three-variable relationship governs the actuation time or the speed of a hydraulic actuator. Flow, for some inexplicable reason, is often conceptually expressed as Q. We are only a couple minutes into this lecture, and a quick scan of 2 units used to measure pressure and flow rate tells us that pressure governs force, and flow rate governs speed. Equally as important, it also tells us that pressure has nothing to do with speed, and flow rate has nothing to do with force. We'll learn throughout the course of this playlist that 3 important properties of hydraulic actuators are governed by 3 independent quantities. Strength of actuation, or force, is governed by pressure. Speed, or actuation time, is governed by flow rate. Direction of actuation is governed by valve position, and you don't need a formula for direction. I'll remain consistent with this summation throughout the course of this playlist. If you can walk away from your experience with this simple understanding, I will consider my time having not been spent in vain. In a short span of time, we've already discussed the 3 most important properties simply by looking at the units of pressure and flow rate. The units used to measure these quantities tell us this simply and directly without any heartbreaking labor. I've got this weird feeling hydraulics, in contrast to electronics, might be, dare I say it, easy? This is not to say that U.S. customary units are not unwieldy or weird. The whole system is based in archaic and weird quantities. Take, for example, the gallon, a unit of volume. you must simply remember that a gallon is equal to a volume of 231 cubic inches. Therefore, using the steps I delineated in the unit conversion lecture, a 10-gallon hat worn by a cowboy with an unusually large head would have a volume of 2,310 cubic inches. One might be tempted to express this volume using engineering prefixes as 2.31 kilocubic inches, but this isn't the practice when using U.S. customary units. Unusually large or unusually small numbers are just that, expressed using U.S. customary units. Unusually large, unusually small, and exceedingly difficult to write, read, and conceptualize. You can't have it all. It is for this reason I'll sometimes perform calculations using U.S. customary units alongside that of their SI metric system equivalents. This lecture series, however, would be prohibitively long if I did so for each and every illustrated example problem. It is therefore incumbent upon you to perform the conversion to the unit system most commonly utilized by your occupation or country. If you are as versed in unit conversions as I expect you to be, the choice of units employed should be of absolutely no concern or consequence. Quantities measured in hydraulics include length, area, volume, pressure, force, flow rate, and time. We'll return to special purpose quantities like velocity and viscosity in later lectures. Units commonly employed in hydraulics to measure these quantities for both systems include inches and centimeters for length, square inches and square centimeters for area, cubic inches or gallons, and cubic centimeters or liters for volume, psi, bar, and kilopascals for pressure, pounds force and newtons for force, gallons per minute and liters per minute for flow rate. Time is measured in seconds for both unit systems, and you should be reasonably savvy enough to understand 1 minute equals 60 seconds. Here are the equivalencies between these units I'll be employing for the purposes of this lecture. This might be a great time to jot these down in your notes. Hint, hint. I've taken some liberties with these conversions and rounded them to a manageable number of decimal places. The inch is directly defined as exactly 2.54 centimeters. The bar is defined as exactly 100 kilopascals, and I've approximated this as equivalent to 14.5 psi. It's good enough for our purposes. Notice I've not directly included a conversion for surface area from square inches to square centimeters, nor volume from cubic inches to cubic centimeters. These are left as illustrated example problems. Speaking of illustrated example problems, here's some illustrated example problems. Pause the lecture and see if you can convert these quantities expressed in the given units to the desired units. Remember, in order to maintain equality, one can always multiply by 1. Choose 1 such that the units you don't want cancel out and the units you do want remain. Our first example problem is asking us to convert an area of 1 square inch to units of square centimeters. There is no direct conversion between square inches and square centimeters in our list. However, we're given the fact that 1 inch equals 2.54 centimeters. As directly implied by the units, an area of 1 square inch is a square 1 inch by 1 inch. If 1 inch is 2.54 centimeters, it stands to conjecture this same area is a square of dimensions 2.54 centimeters by 2.54 centimeters, or 6.4516 centimeters squared. If you wanted to round this off to 3 decimal places, you could say that 1 square inch equals 6.452 centimeters squared, with the understanding that there will be inaccuracies due to rounding errors if you use this number for conversions. Similarly, our second example problem is asking us to convert a volume of 1 cubic inch to units of cubic centimeters. There is no direct conversion between cubic inches and cubic centimeters in our list. However, we're given the fact that 1 inch equals 2.54 centimeters. As directly implied by the units, a volume of 1 cubic inch is a cube 1 inch by 1 inch by 1 inch. If 1 inch is 2.54 centimeters, it stands to conjecture this same volume is a cube of dimensions 2.54 centimeters by 2.54 centimeters by 2.54 centimeters, or 16.387064 centimeters cubed. If you wanted to round this off to 3 decimal places, you could say 1 cubic inch equals 16.387 cubic centimeters, with the understanding that there will be inaccuracies due to rounding errors if you use this number for conversions. Before we move on to the remaining illustrated example problems, let's stop a moment and take a look at these two figures. Flat, 2-dimensional square and a 3-dimensional cube with height. Squares are different than circles. Cubes are different than cylinders. And solids are different than liquids. But regardless of the form of the shape, surface area is measured using units of square inches or square centimeters. And volume is measured using cubic inches or cubic centimeters. This means our unit of area is not a rigid plane of glass, nor our unit of volume an ice cube, but rather an amorphous sheet or a blob that can be cut apart and packed into all those notably non-square corners of circles and cylinders and still give an idea of that circle's surface area or cylindrical volume. It may help you to think about each unit of area as a sheet of paper that can be cut into all sorts of infinitely small, weird shapes. Regardless of the form these sheets take, each square inch of area still has an area of 1 square inch. If you use only half a sheet of paper with an original surface area of 1 square inch to make a shape, that shape has an area of a half square inch. Additionally, it may help you to think about each unit of volume as a quantity of liquid inside a cubic container. If you pour 7.5 cubes full of liquid, each cube measuring 1 inch by 1 inch by 1 inch, to completely fill in a regular 3-dimensional object, that object has a volume of 7.5 cubic inches. It makes a lot of sense if you think about this visually. As interesting an intellectual exercise it has been finding a direct conversion between units of area and volume between these two different systems, it is of limited practical value. Unless you use all decimal places, these conversion factors will be a source of inaccuracy. 1 inch is directly and explicitly defined as 2.54 centimeters. This single number is far easier to remember than 3 separate equivalencies of length, surface area, and volume, each with an increasing number of decimal places. Just remember that 1 inch equals 2.54 centimeters. You'll appreciate this advice when we perform the calculation of circular area and cylindrical volumes in a moment. Moving on. Our next example problem is asking us to divert a quantity of 3.142 cubic inches to gallons. The unit we want is gallons, so this goes on top. The unit we don't want is cubic inches, so this goes on the bottom. The units of cubic inches cancel out, and we're left with a mind-numbing, confusing string of gobbledygook. You needn't be surprised by this number's evident unwieldiness. A gallon is a quantity of 231 cubic inches. 3.142 cubic inches is substantially smaller than a gallon. Therefore, this same quantity of 3.142 cubic inches should be substantially smaller, expressed in units of gallons. It makes sense. If your calculations indicate something smaller than 231 cubic inches has a volume larger than 1 gallon, you're doing it wrong. Always check your results to make sure they make sense. If we wanted to round this number down to 3 decimal places, we could say this object has a volume of 0.014 gallons. However, such a number would introduce cumulative rounding errors if we were to use it in later calculations. My recommendation, consistent with the advice I imparted at the end of the DC Math lecture, is if this number is part of a multi-step calculation, is to use the previous results key on your calculator and let your calculator wield it in all its unwieldy glory, and only round your final result to the required number of decimal places. Our next example problem is asking us to convert a quantity of 115.8 cubic centimeters to liters. The unit we want is liters, so this unit goes on top. The unit we don't want is cubic centimeters, so this goes on the bottom. The units of cubic centimeters cancel out, we're left with a number 0.1158 liters. The conversion from cubic centimeters to liters and from liters to cubic centimeters is based upon the shift of the decimal point 3 places rather than some archaic quantity, as it is when converting between cubic inches and gallons and vice versa. This is super easy. The only problem people have is that they are rightly tempted to employ engineering prefixes to this number and call it 115.8 milliliters. This is correct. However, for our purposes for the hydraulics playlist, I'm actually recommending you not take this step and simply use the units I recommended for length, area, volume, flow rate, and so on. This prevents the possibility of you entering 115.8 into your calculator when you mean 0.1158. You'll understand the utility of remaining consistent with units when we start discussing calculation of hydraulic quantities. Our next example problem is asking us to convert a quantity of 5,500 kilopascals, which could also be rightly written as 5.5 megapascals, to both bar and psi. To convert to bar, the unit we want is bar, so it goes on top. The unit we don't want is kilopascals, so this unit goes on the bottom. The units of kilopascal cancel out, and we're left with the number 55 bar. The bar, notice it's pronounced bar in both singular and plural form, is a handy means of pressure measurement. Not only because it's roughly equivalent to 1 atmosphere of pressure, it's also a handy intermediary between US customary units and SI metric units and vice versa. Converting this same quantity of pressure from bar to psi, the unit we want is psi, so it goes on top. The unit we don't want is bar, so this goes on the bottom. The units of bar cancel out, and we're left with the number 797.5 psi. Again, don't freak out when your pressure gauge's needle points to the general vicinity of 800 psi. Our next example problem is kind of a remix of the preceding example with slightly different lyrics. It's asking us to convert a quantity of 21 bar to both kilopascals and psi. To convert to kilopascals, the unit we want is kilopascals, so it goes on top. The unit we don't want is bar, so this goes on the bottom. The units of bar cancel out, and we're left with the number 2,100 kilopascals. If you wanted to, you could rightly call this same quantity of pressure 2.1 megapascals using engineering prefixes. However, for our purposes, kilopascals is our desired unit. I've not directly given you a means of converting straight from kilopascals to psi, although such means do exist. My question is, why would you ever want to remember more numbers when only a handful, used in a logical fashion, can get the job done just as easily? The point is, you don't need a hardware store to fix every problem. Sometimes a reasonably sized toolbox filled with useful multi-purpose tools does the job just as well with less of a chance of busting an O-ring when you try to pick it up. In this case, we can step back to our original quantity of 21 bar and convert this to psi. The unit we want is psi, so it goes on top. The unit we don't want is bar, so this goes on the bottom. The units of bar cancel out, and we're left with the number 304.5 psi. Again, don't freak out when your pressure gauge's needle points to the general vicinity of 300 psi. This next example problem is a remix of the remix, and I feel confident you should be able to arrive at the numbers 35.2 bar rounded to the tenths place and 3,517.2 kilopascals rounded to the 10th place. Let's do one last unit conversion involving flow rate. Here we're being asked to convert a flow rate of 2 gallons per minute to liters per minute. We're again not given any direct conversion between gallons per minute and liters per minute. We are, however, given the fact that 1 gallon equals approximately 3.785 liters. Since units of flow rate are both being divided by the same quantity of time, a minute, it stands to conjecture this single volumetric equivalency brings with it a bonus equivalency of flow rate. That of 1 gallon per minute equals approximately 3.785 liters per minute. To convert a flow rate of 2 gallons per minute to units of liters per minute, the unit we want is liters per minute, so it goes on top. The unit we don't want is gallons per minute, so this goes on the bottom. The units of gallons per minute cancel out, and we're left with a flow rate of 7.57 liters per minute. Let's put aside unit conversions for a moment and discuss the calculation of circular area and cylindrical volume. This is an exceedingly important section because the principal linear actuator employed in hydraulic systems, the hydraulic cylinder, is, as the name implies, cylindrical in shape. As discussed in the hydraulic cylinders lecture, available at the Big Bad Tech channel, A hydraulic cylinder has a circular cap end with a given diameter, d cap, and when fully extended, the cap end volume is cylindrical in shape with a given travel length, h. The three-dimensional volume of the cylindrical cap end at full extension would therefore be the area of the cap, the red circle, times its travel length. V cap, the blue volume, is equal to the area of the cap, the red circle, times the travel length, h. We'll discuss how the diameter of the cap influences the area of the cap in a moment. Equally valid is that upon retraction, the effective area of the rod end, notice the term I'm using, rod end, has a ring-like or annular area equal in diameter to that of the cap. However, it has a circle removed from the center, where this circle has a diameter equal to the diameter of the rod. It can be said, therefore, that the area of the rod end, the ring, has an area of the cap end, the big circle, minus that of the area of the rod, the small circle in the center. The area of the rod end equals the area of the cap end minus the area of the rod. Notice the term I'm using. The cap end is the big circle. The rod end is the ring. The rod is the small circle. You simply must remember these facts, understand their significance, and differentiate between these terms. By all means, draw a picture. Think visually. Additionally, at full retraction, as the term implies, the rod is retracted into the rod end of the cylinder. That, by the way, is why they call it the rod end. It's the end with the rod. This rod is solid and displaces a quantity of hydraulic fluid equal to the volume of the rod. It makes sense, then, that the volume of the rod end is a cylinder with a cylinder removed from the center, or a tube. The volume of this tube can be expressed as the volume rod end equals the volume of the cap end minus the volume of the rod, where the volume of the rod is equal to the area of the rod times the travel length, h. Equally valid is the observation that the volume of the rod end should also be equal to the area of the rod end times the travel length, and both methods of calculating the volume of the rod end should yield the same result. These images make sense. I'm suggesting you take the time to copy them down on your notebook and clearly attach the terms associated with them, since we'll be applying these terms and calculating these values on a regular basis from this point forward. The cap end has a diameter, d cap, and an area of a cap. The rod has a diameter, d rod, and an area of a rod. It is also a full circle, but it is much smaller than the cap end. The rod end is the cap end with the rod removed from the center. It is a ring. The cap end at full extension is a full cylinder and occupies a volume of a cap times the travel length, h. The rod is also a full cylinder and it occupies a volume of a rod times the travel length, h. The rod end at full retraction is tubular in shape. It is the volume of the cap end minus the volume of the rod removed from consideration. Additionally, it can be said that this space is also equal in volume to area of the rod end times the travel length, h. Remember this diagram. Remember these terms. Truly, half of hydraulics is the simple understanding how the physical construction of the hydraulic cylinder impacts speed and force of extension versus speed and force of retraction. The other half is all the cunning ways we can use various fluid power devices to control flow, pressure, and direction, to use them to perform useful work. Hydraulics and electrical control of hydraulic systems, as you'll see, is a really neat integration of the electrical, mechanical, and hydraulic aspects of a system. We've discussed these shapes in terms of the most general variety. However, we've got to go into some detail about calculating numerical values. It should come to you as no surprise that circles are different than squares. Squares of the same width have more surface area than circles of the same diameter because the corners are taken into consideration. You can also be rightly said that circles of the same diameter have less surface area as squares of the same width because the corners are outside the perimeter of the circle and not taken into consideration. Tracking so far? Circular areas are calculated using the transcendental number pi. Pi is a constant, yet irrational number, being 3.1415, blah blah blah. Two common formulas exist to calculate the surface area of a circle are area equals pi r squared and area equals pi over 4 d squared. I am emphatically recommending you use this one and not the other. The first circular surface area formula uses radius, where the radius r is a measurement of a circle from the circle's center to its edge. Diameter, d, is a measurement of a circle's edge to edge passing through the center. It makes sense then that radius is only half of diameter. That's great and true, but dimensions of hydraulic actuators, hoses, and electrical wires are normally given in terms of diameter and not radius. Why perform unnecessary calculations when a single formula will yield the same result in a single step? For those of you still not convinced, these two formulas are equivalent, and I'll prove it to you. All you need to do is substitute radius equals diameter divided by 2 in the first formula. Notice I've enclosed d over 2 in parentheses. It makes it very clear that the entire quantity, which was previously represented by just r, is to be squared. You can leave it as such, however it's often recommended to perform operations and group constants together to make it easier to solve when you insert the observed values. To this end, d over 2 can be broken apart into 1/2 times d, both of which are being squared. 1/2 squared is a quarter. D squared is still d squared. This still isn't the prettiest formula because pi, despite the fact I'm using a symbol to represent it, is actually a constant. It's normally recommended to group constants together for a final rendition of area equals pi over 4 times diameter squared. This is the formula I want you to use. Again, the dimensions of electrical wires and hydraulic cylinders and hoses are often presented in terms of diameter and not radius. If you use this formula to solve for area, you never have to go through algebraic manipulations to solve for area. You simply square the diameter, then multiply this by pi, then divide this quantity by 4. Additionally, since pi is a constant, depending on your degree of desired accuracy, you'll often see this same formula represented as 0.7854 d squared, where 0.7854 is a reasonable approximation of pi over 4. There's a teeny bit of error when you use such approximations. However, as we'll soon learn, the error is of such small magnitude is often of absolutely no significance. Let's put our understanding of circular surface area to the test. Pause the lecture to see if you can solve for the desired quantity using the given units. Note illustrated example problems 3 and 4 are expressing diameter in one unit system and asking for surface area in another. Don't blindly stumble into this pit trap. Example problem 5 is a little different than any of the others and will require some thought coupled with your knowledge of algebraic manipulation. Come up with a plan and execute it violently. Our first illustrated example problem gives us a diameter in inches and asks us to solve for the surface area in units of square inches. Too easy. Bust out the area formula, pi over 4 d squared, and plug and chug. Substituting the necessary values, we're left with something I can round off to 1.767 square inches if I so desired. Notice despite this being a circle, the units of area are square inches. Additionally, notice I calculated this number using the purest form of pi over 4 my calculator was capable of representing. If, however, I wish to approximate pi over 4 as 0.7854, this same calculation yields a value of 1.76715 square inches. Which answer is correct? Neither. They're both approximations since they both use approximations of pi. For our purposes, however, the differences are negligible. Use whichever method you feel more comfortable with. Pi over 4 or 0.7854 are, for our purposes, the same thing. This being said, if this was part of a multi-step calculation, using this previous result via the previous results key on your calculator would yield more accurate results, and the final answer could be rounded off to the appropriate decimal place. Our second illustrated example problem is almost identical to the first. The only difference between the numbers and the choice of units. Area still equals pi over 4d squared. Substituting in the necessary values, we're left with something I can round off to 5.067 square centimeters if I so desired. Again, if I wish to approximate pi over 4 as 0.7854, the same calculation yields a value where any difference is encountered 5 decimal places out and beneath our level of concern. The next illustrated example problem is giving us a diameter in units of inches and asking us to solve for surface area in terms of square centimeters. You have two options when presented with such a problem. You can solve it the hard way or the easy way. The hard way has you solve for surface area in given units, then converting area to the desired unit system. A far easier approach is to convert given units to desired units right up front, and from there solve for surface area. This is the easy way because 1 inch is defined as 2.54 centimeters. You can remember and retain the fact that 1 inch equals 2.54 centimeters, but I sincerely doubt you'll be able to remember and retain surface area and volumetric equivalents to any degree of accuracy or reliability. Remember, a tiny toolbox filled with multi-purpose tools can do the job of every tool in the tool shed if you use them wisely. 5/8 of an inch is 0.625 inches. Again, this is one of those archaic throwbacks of the US custom-era unit system. Not only did peasants lacking TI-89 titanium edition graphing scientific calculators use archaic units, they had to think in fractional representations of weird units. To convert this quantity of inches to centimeters, the unit we want is centimeters, so it goes on top. The unit we don't want is inches, so this goes on the bottom. The units of inches cancel out, and we're left with a diameter of 1.875 centimeters. You might be tempted to round this off to 1.588 centimeters, but that is not in accordance with my previous recommendations regarding multi-step calculations. Don't round it off. Don't re-enter it. Let the calculator do the heavy lifting for you, and use the previous results key. Substitute this into the area formula, pi over 4 d squared. We're left with an answer I can round off to 1.979 square centimeters. This next illustrated example problem is astoundingly similar. We're given a diameter in units of centimeters and being asked to solve for surface area in terms of square inches. Let's do it the easy way and convert centimeters to inches right up front. The unit we do want is inches, so it goes on top. The units of centimeters is what we don't want, so it goes on the bottom. The units of centimeters cancel out, and we're left with a diameter of 0.5 inches, or half an inch if you're a non-decimal system using peasant stuck in the Dark Ages. Substituting this into the area formula, pi over 4 d squared, we're left with an answer I can round off to 0.196 square inches if I so desired. The last illustrated example problem is ever so slightly different. In this case, we're given an area value in terms of square inches, and we're asked to solve for the diameter in terms of inches. Your choice, the hard way or the easy way. The hard way would have us substitute the number 7.069 square inches in place of area, and make us drag it around all day from place to place like an 8-foot log, limbs attached. The easy way would have us rearrange the formula at the conceptual level, and only after we've arrived at our desired form would we plug in the given 7.069 square inches. Our goal is to maintain equality and somehow isolate d on one side of the equation. We'll start by multiplying both sides by 4. 4 cancels out on the right-hand side. Now we'll divide both sides by pi. Pi cancels out on the right-hand side. d is by itself, but we have not arrived at the solution yet because d is still being operated on by being raised to the second power. We can cancel out this operation by square rooting both sides. The square root of d squared is d, leaving us with d equals square root of 4 times area divided by pi. Notice the radical is encompassing all of 4a divided by pi. Not just 4, not just the top half, all of it. We can make this exceedingly obvious by enclosing 4a divided by pi in parentheses, indicating that the radical is acting on all of it. Again, you can leave it like this. However, it's sometimes helpful to remove those constants that are easily square rooted out from under the radical. The square root of 4 is 2, So d is also equal to 2 times the square root of area divided by pi. Again, the square root encompasses both a over pi, not just the top half. It can be made exceedingly obvious using parentheses. The parentheses might seem unnecessary when you're writing these equations out on paper. However, they're not only handy, they're absolutely necessary when entering such equations into a calculator. We can now substitute in our given area of 7.069 square inches and press enter. The calculator yields a result of 3.00008838899 inches, which is totally wrong. You don't make hydraulic cylinders with 3.00008838899 inch diameters. They do, however, make hydraulic cylinders with 3-inch diameters. The point is, the surface area I gave you, 7.069 square inches, is an approximation of the surface area of a circle with a 3-inch diameter. There's a tiny disjoint in our answers because of the approximation. You've got to be extremely hard-headed to not understand that a diameter of 3.00008838899 inches means 3 inches. Watch out for this and don't freak out. If you are freaking out, snap out of it. Quit being so uptight and inflexible. Be cool, be flexible, and be aware of this. Cool people approximate, can make logical and rational deductions. Robot-like automatons tediously nitpick, freak out, and post comments like, "Your maths are bad," in all caps using flawed grammar and fractured spelling. Stay task-oriented and mission-focused. Efficient and effective engineering education necessitates we make approximations. My advice is to simply deal with it. Moving on, let us now add a twist, or more appropriately, a hole to our calculations of surface area. Let's say a circular region of space has been removed from the center of another circle. Pay attention to this, because this will become exceedingly important when we apply this to the functional area of retracting cylinders. Use the circular surface area to solve for the remaining ring-like or annular surface area for these illustrated example problems. Our first example is in effect asking us to subtract the area we solve for in problem 4 from the area we solve for in problem 1 in our previous circular area illustrated examples. This would be the effective area of the rod end for a cylinder with a cap end diameter of 1.5 inches and a rod diameter of 1/2 inch. If you went to the trouble of recalculating this data, or just went back up and used the previous results from the circular area illustrated examples, you should find this ring-shaped rod end has a surface area of approximately 1.571 square inches rounded to 3 decimal places. Again, if you use the rounded figures from your previous calculations to arrive at the solution, you'd be ever so slightly off. Use the unrounded figures for intermediate calculations and only round your final result. Our second illustrated example problem is in effect asking us to subtract the area we solve for in problem 3 from the area we solve for in problem 2. This would be the effective area for the rod end of a cylinder with a cap diameter of 2.54 centimeters, or 1 inch, and a rod diameter of 1.5875 centimeters, or 5/8 of an inch. If you went to the trouble of recalculating this data, or just went back up and used the previous unrounded results, you should find this ring-shaped rod end area has a surface area of 3.0088 square centimeters rounded to 3 decimal places. Let us now enter the third dimension and calculate the cylindrical volume of complete cylinders and cylinders with a cylindrical portion removed from the center. You'll be happy to know this is a very easy task. The volume of a cylinder is simply the area of the circular face times its height. Consider our first example, where a cylinder has a diameter of a cap of 1.5 inches, the diameter of the rod of 1/2 inch, and a travel length of 6 inches. Using our previous understanding of circular surface area, a 1.5 inch diameter circle has a surface area of pi over 4 d squared. This quantity times a height of 6 inches means this full cylinder has a volume of 10.603 cubic inches rounded to 3 decimal places. If this cylinder had a cylindrical core with a diameter of a ½ inch removed from it, this is effectively asking us to subtract the volume of the ½ inch diameter core with a height of 6 inches from our original 1½ inch diameter cylinder with a height of 6 inches. Alternately, one can calculate the volume of this tube by taking the area of the rod end times the height of 6 inches. Substituting in the unrounded previous results, either calculation would yield an answer we can round to 9.425 cubic inches. Notice how I repeatedly used the most accurate version of previously obtained results, thereby saving me time and freeing me from transcription errors and accumulating inaccuracies. Our second problem is using a cylinder with a cap diameter of 2.54 centimeters, a rod diameter of 1.5875 centimeters, and a travel length of 10.16 centimeters. Whether you went to the trouble of recalculating these values or substituted in the previous unrounded results, we're left with a full cylindrical volume we can round to 51.481 cubic centimeters. If this full cylinder had a cylindrical core with a diameter of 1.5875 centimeters removed from it, this is effectively asking us to subtract the volume of the 1.5875 diameter core with a height of 10.16 centimeters from our original 2.54 centimeter diameter cylinder with a height of 10.16 centimeters. Alternatively, one can multiply the annular rod end area times the height of 10.16 centimeters. Whether you went to the trouble of recalculating these values or just re-entered the unrounded previously obtained results, this yields a volume we could round to 31.372 cubic centimeters. Again, notice how I use the same formulas in the same sequence and repeatedly use the most accurate version of previously obtained results, thereby saving me time and freeing me from transcription errors and accumulating inaccuracies. You'll be happy to know that functional areas and volumes for all hydraulic cylinders are always calculated in this same manner, and I am not going to bait and switch you. Learn how to do so efficiently and effectively today, and the rest of the hydraulics playlist will be very easy. In this spirit, here are a couple example problems that make use of these techniques. Pause the lecture and attempt to solve for the surface area of the cap end, the big circle, the surface area of the rod, the small circle, the surface area of the rod end, the ring, using the given unit system. Additionally, solve for the volume of the cap end at full extension, the full cylinder, and the volume of the rod end at full retraction, the full cylinder with the rod removed, or the tubular volume. I'll not go into details for the calculations since the two previous illustrated example problems already did so. Let's round our answers to 3 decimal places and remember to use the previous results key to make it easy on yourself and ensure your answers don't accumulate inaccuracies. Our first example has a cylindrical actuator with a 3-inch cap diameter. This presents a 7.069 square inch surface area. The rod has a ½ inch diameter. The rod has a surface area 0.196 inches squared. The rod end, the ring, is the area of the cap minus the area of the rod and presents a functional surface area of 6.872 inches squared. The volume of the cap end at full extension is 42.412 inches cubed. The volume of the rod end at full retraction is equal to the volume of the cap end minus the volume of the rod, or the area of the rod end times the travel length. Either way, this presents a volume of 41.233 cubic inches. Our second example has a cylindrical actuator with an 8.89 centimeter cap diameter. This presents a full circular surface area of 62.072 centimeters squared. The rod has a surface area of 2.850 centimeters squared. The rod end, the ring, is the area of the cap minus the area of the rod and presents a functional surface area of 59.221 centimeters squared. The volume of the cap end at full extension is 945.972 centimeters cubed. The volume of the rod end at full retraction is equal to the volume of the cap end minus the volume of the rod, or the area of the rod end times the travel length. Either way, this presents a volume of 902.535 centimeters cubed. Our third illustrated example has a cylindrical actuator with a 2¼ inch cap diameter. This presents a surface area of 3.976 inches squared. The rod has a 7/8 inch diameter. The rod has a surface area of 0.601 inches squared. The rod end, the ring, is the area of the cap minus the area of the rod. Presents a functional surface area of 3.375 inches squared. The volume of the cap end at full extension is 31.809 inches cubed. The volume of the rod end at full retraction is equal to the volume of the cap end minus the volume of the rod, or the area of the rod end times the travel length. Either way, this presents a volume of 26.998 cubic inches. Our last illustrated example is a cylindrical actuator with a 5 centimeter cap diameter. This presents a surface area of 19.635 square centimeters. The rod has a 2 centimeter diameter. The rod has a surface area of 3.142 square centimeters. The rod end, the ring, is the area of the cap minus the area of the rod, and presents a functional surface area of 16.493 square centimeters. The volume of the cap end at full extension is 392.699 centimeters cubed. The volume of the rod end at full retraction is equal to the volume of the cap end minus the volume of the rod, or the area of the rod end times the travel length. Either way, this presents a volume of 329.867 cubic centimeters. Moving on, let us now discuss flow rate, volume, and time. As previously mentioned, flow rate is a given unit of volume, either gallons or liters, of some fluid entering or leaving a space over a period of time in units of minutes. A rearrangement of these units tells us that volume is a unit of flow rate times unit of time. Another equally valid rearrangement of these units tells us that time is units of volume divided by units of flow. This three-variable relationship governs the actuation time or speed of a hydraulic actuator. Using the figures from the previous illustrated example problems, let's determine how long it takes in seconds to fill a space of a given volume for a constant flow rate. Our first example is asking us to solve for both the extension and retraction time for a cylinder of the following dimensions. The diameter of the cap is 3 inches, the diameter of the rod is a 1/2 inch, and the travel length is 6 inches. Let's say the flow rate is a 1/2 gallon per minute. Using one permutation of our flow rate, volume, and time relationship, it can be said that time is equal to volume divided by flow rate. On a general conceptual level, this should be readily understood. It's the details that matter. First, the flow rate is given in units of gallons per minute, and the volume is expressed in cubic inches. Second, the flow rate is expressed in units of minutes. And the question, if we remember correctly, was asking us for the time in units of seconds. One must properly convert between units if the answer is to make any sense. Additionally, one must differentiate between which space is filled for each action. The act of extending the cylinder means one is filling the cap end, the full cylinder. The act of retracting a cylinder means one is filling the rod end, not the rod end, the cylinder with the cylinder removed, or the tubular volume. Stay organized. Use a diagram with all the terms and formulas attached. Visualize the act of extension and how it differs from retraction. The tubular or rod end has a smaller volume than the cap end. Given a constant flow rate entering these different volumes, start thinking now of how long it will take to fully extend a rod and compare it to how long it would take to fully retract the rod. Will extension take more, less, or the same time as retraction? Conversely, will retraction take more, less, or the same time as extension? Just think about this. No numbers. Which act is faster for a double acting cylinder for a constant flow rate? If you're on the right track, You said retraction should occur faster than extension. Faster retraction speed means it takes less time to do so because there's less volume to fill in comparison to the cap end without the volume of the rod removed. It makes sense. We haven't used any numbers. Now, just put some numbers in there. Your choice. Convert the volume you want to fill to units of gallons, or convert your flow rate to units of cubic inches per minute. And again, for extension, our volume of interest is the cap end. For retraction, our volume of interest is the rod end. I'll start by converting our flow rate from gallons per minute to units of cubic inches per minute. Units of gallons per minute cancel out, and we're left with a flow rate of 0.5 gallons per minute, being equal to 115.5 cubic inches per minute. Given time equals volume divided by flow rate, and substituting in the necessary unrounded values, units of cubic inches cancel out, and we're left with a time in units of minutes. This can be converted to seconds with the understanding that 1 minute equals 60 seconds. Units of minutes cancel out, we're left with an extension time of 22.0 seconds rounded to the tenths place. For retraction time, our volume of interest is the rod end, not the rod end. Substituting in the unrounded values, units of cubic inches cancel out, and we're left with a time in units of minutes. This can be converted to seconds with the understanding that 1 minute equals 60 seconds. Unit of minutes cancel out, we're left with an extension time of approximately 21.4 seconds rounded to the tenths place. Notice retraction time is less than extension time, as we previously pontificated. It makes sense. The solid rod occupies space inside the rod end when it's retracted. Therefore, the quantity of fluid required to fill this space is less. If fluid enters the space at a constant rate, it would take less time to completely fill it in comparison to the cap end. Before we move on to an additional illustrated example problem, pause to consider extension and retraction speed, and compare it with extension and retraction time. Speed is a measurement of distance over time. If we assume the extension and retraction distance to be the same as travel length, in this case 6 inches, the calculation of extension and retraction speed is a trivial matter given we've already solved for time. If at full extension the rod travels 6 inches over the time span of approximately 22.0 seconds, it can be said that the rod is extending at a speed of approximately 0.272 inches per second, rounded to the tenths place. Notice I'm using the unrounded version of extension time to calculate this figure. If during full retraction the rod travels 6 inches over a time span of 21.4 seconds, it can be said that this rod is retracting at a speed of 0.280 inches per second, rounded to the thousandths place. It makes sense. Something that extends the same length over a longer time moves slower than something that retracts the same length over a shorter time. Increasing time decreases speed. Decreasing time increases speed. Just as valid, one can say that increasing speed decreases time, and decreasing speed increases time to travel the same distance. Let's make some room here and try a second example. This second example is asking us to solve for both the extension and retraction time for a cylinder with the following dimensions, given a constant flow rate of 3 liters per minute. The cap diameter is 8.89 centimeters. The rod diameter is 1.905 centimeters, and the travel length is 15.24 centimeters. Let's first convert the constant flow rate of 3 liters per minute to units of cubic centimeters per minute. Units of liters per minute cancel out. We're left with a flow rate of 3 liters per minute being equal to 3,000 cubic centimeters per minute. Let's solve for extension time first. Stay organized. The act of extending a cylinder means one is filling the cap end, the full cylinder. Substituting in the necessary unrounded values, units of cubic centimeters cancel out, and we're left with time in units of minutes. This can be converted to seconds with the understanding that 1 minute equals 60 seconds. Unit of minutes cancel out, and we're left with an extension time of approximately 18.9 seconds. The act of retracting a cylinder means one is filling the rod end, not the rod end, the cylindrical volume with the cylinder removed from the center. Substituting in the necessary unrounded values, units of cubic centimeter cancel out and we're left with a time in units of minutes. This can be converted to seconds with the understanding that 1 minute equals 60 seconds. Units of minutes cancel out and we're left with an extension time of approximately 18.1 seconds. Notice retraction time is less than extension time. Again, consider extension and retraction speed. Given the rod extends and retracts a constant distance of 15.24 centimeters, we can say it is extending at a speed of approximately 0.806 centimeters per second and retracting at a speed of approximately 0.844 centimeters per second. Less time to retract means retraction speed is greater than extension. It makes sense. I must reiterate, all these speed and time calculations make use of unrounded previous results, and only the final answer is rounded to the desired place. 15.24 centimeters divided by 18.1 seconds using the approximated value of 18.1 seconds rather than the unwieldy previous results is actually 0.842 centimeters per second. You're still getting an answer really close to what you'd expect, and any difference is really kind of negligible. However, use previous results and only round your final answer. I think I'm just going to stop saying this and establish it as a standard operating procedure from this point forward. Use previous results and only round your final answer. This standard operating procedure having been officially established, pause the lecture and take a shot at these two illustrated example problems. Determine the extension time, the retraction time, and the extension speed and the retraction speed in the given units for the given flow rates. Problem 3 uses a cylinder with these dimensions: the diameter of the cap of 2¼ inches, a diameter of the rod of 7/8 of an inch, and a travel length of 8 inches, with a flow rate of 1.5 gallons per minute. Problem 4 uses a cylinder of these dimensions: a diameter of the cap of 5 centimeters, a diameter of the rod of 2 centimeters, and a travel length of 20 centimeters, with a flow rate of 2.5 liters per minute. I won't go into great detail about these calculations since the steps are exactly the same as our previous illustrated example problem. The third illustrated example problem should have an extension time of approximately 5.5 seconds, a retraction time of 4.7 seconds, an extension speed of 1.45 inches per second, and a retraction speed of 1.71 inches per second. Our fourth example problem should have an extension time of approximately 9.4 seconds, a retraction time of 7.9 seconds, an extension speed of 2.12 centimeters per second, and a retraction speed of approximately 2.53 centimeters per second. The next topic related to flow rate is something known as displacement. Pumps, as we'll learn in later lectures, provide flow to a fluid power system. Every single revolution of the pump will displace a certain volume of fluid, expressed in units of cubic inches per revolution or cubic centimeters per revolution. The shaft of the pump is driven by a prime mover, either an electric motor or an internal combustion engine that rotates the shaft at a rotational speed, typically measured in units of revolutions per minute, or RPM. Algebraic manipulations at the unit level suggest that if volumetric displacement per revolution is multiplied by revolutions per minute, the units of revolution cancel out, and we're left with units of volume divided by units of time. Volume over time is a unit of flow rate. If displacement per revolution is held constant and rotational speed is increased, flow rate increases. If displacement per revolution is held constant and rotational speed is decreased, flow rate decreases. If rotational speed is held constant and displacement per revolution is increased, flow rate increases. If rotational speed is held constant and rotational displacement per revolution is decreased, flow rate decreases. It makes sense. Only thing that can possibly trip you up is neglecting to perform a unit conversion. Allow me to demonstrate. Let's say a pump displaces 0.28 cubic inches per revolution and is driven at 1,800 RPM. If we multiply displacement per revolution times rotational speed, the units of revolution cancel out, and we're left with a flow rate of 504 cubic inches per minute. If we want to convert this to gallons per minute, we'd have to do a unit conversion, where 504 cubic inches per minute is equal to approximately 2.18 gallons per minute. Let's say another pump displaces 5 cubic centimeters per revolution and is driven at 1,500 RPM. If flow rate is displacement per revolution times rotational speed of revolutions per minute, units of revolution cancel out, we're left with 7,500 cubic centimeters per minute. If we wanted to convert this to units of liters per minute, we'd find the flow rate of 7,500 cubic centimeters per minute is equal to 7.5 liters per minute. Here's 2 remaining illustrated example problems left for you to attempt on your own. Pause the lecture and take your best shot. Use the given displacement and rotational speed to determine the flow rates in either units of gallons per minute for pump A and liters per minute for pump B. If you've done everything correctly, pump A should be producing approximately 192 cubic inches per minute, which is approximately 0.83 gallons per minute, and pump B should be producing 4,400 cubic centimeters per minute, which is a flow rate of 4.4 liters per minute. Let's close out this lecture with a brief inspection of force, pressure, and area calculations. As previously mentioned, a cursory analysis of the units employed by the U.S. customary system, pounds force per square inch, or PSI, directly tells us that pressure is force over area. Given pressure applied to an area, one calculates force as the product of pressure times area. Units of area cancel out and we're left with units of force. More pressure on a constant area means more force. Less pressure on a constant area means less force. Constant pressure on a larger area means larger force. Constant pressure on a smaller area means a smaller force. It makes sense. Using U.S. customary units, nothing could be simpler. If a pressure of 500 pounds per square inch is applied to an area of 1.3 square inches, this means 650 pound force of force is being exerted. Too easy. The units of area, square inches, directly cancel out. Using the SI metric system with engineering prefixes, it's not nearly as easy. This is the one occasion the SI metric system is slightly more cumbersome than the US customary system. And to tell you the truth, the SI metric system is not at fault, but rather the choice of units employed by manufacturers is to shoulder the blame. The centimeter, despite a snazzy prefix and a name drop, is not an SI metric unit, nor is the centi prefix even an engineering prefix. It's a midway station between the base unit meter and the next highest proper engineering prefix, the kilometer. Add to this difficulty the SI metric system unit of pressure, the Pascal, is defined as the SI metric unit of force, the Newton, applied to a square meter. This is why Pascals are so comically small. A Newton of force is equivalent to a fairy diddling a ladybug. When you spread such a minute amount of force over a square meter, almost 10.8 square feet, no wonder it takes close to 6,894.8 pascals to equal a single psi. This means that areas expressed in square centimeters do not directly convert to force when multiplied by pressure, since pressure is measured using a square meter standard. This necessitates an annoying but necessary conversion. 1 meter is equivalent to 10,000 square centimeters. If that wasn't enough, since the Pascal is so comically small, pressure is typically measured in units of kilopascals, where 1,000 pascals is equal to 1 kilopascal. Long story short, the conversion from square centimeters to square meters and from kilopascals to pascals run headlong into each other, such that 10 times the force equals the pressure times the area. Given this merry-go-round of conversion could get confusing at times, I like to think of the 3-variable relationship between force, pressure, and area when expressed in the quasi-SI metric system units of newtons, kilopascals, and square centimeters as requiring an extra 10 in the force position. This accounts for any conversions up or down, and the 10 can be repositioned as needed. Let's say we're being asked to solve for the force in newtons produced by an area of 8 square centimeters when acted on by a pressure of 5,000 kilopascals. Using these units, 10 times force equals pressure times area. Dividing both sides by 10, we're left with force equals pressure times area divided by 10 using the units of kilopascals and square centimeters. Substituting in the necessary values, we're left with 4,000 newtons or 4 kilonewtons of force. This is tricky, and I don't like it any more than you, but rest assured, I'd much rather keep track of the number 10 than any archaic holdover from an agrarian society like gallons, acres, furlongs, firkins, or fortnights. You'd also get the same answer if you directly converted pressure to pascals and area to square meters, but I find throwing an extra 10 in our Pascal's law relationship is a lot easier because it accomplishes the same task in a single step. Be aware engineering prefixes may present pressures in units of megapascals, where 1 megapascal is 1,000 kilopascals. The incorporation of 10 in our 3-variable Pascal's law relationship necessitates force be measured in newtons, pressure in kilopascals, and area in square centimeters. So you'd have to do the necessary conversion from megapascals to kilopascals. As we'll soon discuss at great length in the Pascal's law lecture, the force of extension exerted by a hydraulic cylinder is governed by the pressure input to the cap end of the cylinder and acting upon the full cap face. Similarly, the force of retraction is governed by the pressure input to the rod end of the cylinder and acting not upon the full cap face, but rather the full cap face with the central portion removed from consideration. At retraction, the input pressure acts only upon the smaller, ring-like rod end area, not the rod end, the ring-like portion. Pause to consider what this implies. As we demonstrated in our earlier discussions on flow rate, there should be a difference between extension and retraction forces. Input pressures being equal, the cylinder at extension has more area and will output more force. At retraction, there is less functional area and will output less force. It makes sense. We haven't used a single number. Now, just put some numbers in there. Consider these 4 cylinders with the following dimensions and the following input pressures. Pause the lecture and see if you can determine the force of extension and the force of retraction. Our first cylinder has a cap diameter of 3 inches and a rod diameter of a ½ inch with an input pressure of 530 psi. Extension force is governed by the area of the cap end. Substituting in the unrounded value of the cap end area, we find the force at extension is 3,746.3 pounds force. The force of retraction is equal to the input pressure times the rod end area, not the rod, the ring-like area, the rod end. Substituting in the unrounded values, we found a retraction force of approximately 3,642.3 pounds force. Notice the output force while retracting is slightly less than that of extension given identical input pressures. The area imbalance between the cap end and the rod end account for this difference. There is more functional area in a 3-inch diameter full circle than there is in a 3-inch diameter circle with a ½ inch diameter circle punched out of the center. It makes sense, and it is never going to not make sense if you think of this visually. Draw pictures, take notes, stay organized. The rest of hydraulics should be very easy once you get past the common trip hazards and pitfalls. Consider yet another cylinder with the following dimensions. It has a cap diameter of 8.89 centimeters, a rod diameter of 1.905 centimeters, and an input pressure of 4 megapascals, or 4,000 kilopascals. Given this example is presented in quasi-SI metric units, we need to account for conversions between pascals and kilopascals and square centimeters and square meters by incorporating a 10 into our 3-variable relationship when pressure is measured in units of kilopascals and area is measured in units of square centimeters. At extension, the functional area is the full cap face. Substituting in the unrounded value, we find an extension force of approximately 24,828.7 newtons, or 24.8 kilonewtons. At retraction, the functional area is the rod end. not the rod, the ring-like area, the rod end. Substituting in the necessary values, we find a retraction force of approximately 23,688 newtons, or approximately 23.7 kilonewtons. Again, notice the output force while retracting is slightly less than that of extension given identical input pressures because the functional area of the rod end is smaller than the functional area of the cap end. You're on your own for the last set of illustrated example problems for force, pressure, and area calculations. Solve for extension and retraction force. The third cylinder with an input pressure of 860 psi will extend with a force of 3,419.4 pound force and retract with a force of 2,902.3 pounds force. The last illustrated example problem should have the cylinder extending with a force of approximately 11.8 kilonewtons and retracting with a force of approximately 9.9 kilonewtons. That's it. I know this lecture is a little long and full of math, but trust me, hydraulics doesn't get much harder than this at the level we intend to discuss it. If you think about it, the math I'm asking you to do isn't so hard. It's unit conversion. It's solving for circular area, annular area, cylindrical volume, and tubular volumes. It's rearranging three variable relationships. It's staying organized. The cap end has more functional area than the ring-like rod end. The rod is not the rod end. The cylindrical cap at full extension has more volume than the tube-like rod end at full retraction. These area and volumetric differences account for slower extension speeds and greater extension forces, and faster retraction speeds, yet weaker retraction forces. It makes sense if you think about this visually and just stay organized. Trust me, it won't get much harder than this. All cylinders are cylindrical in shape, and they all use the same formulas and techniques. Just get through this lecture, and the rest of this playlist should be a breeze. As an assessment exercise, I leave you with the following. If you can correctly solve for the following quantities in terms of the desired units, you have met the standards of success for this lecture and are free to move on to the next section. If not, I suggest you revisit the portion of the lecture you're having trouble with and reassess yourself when you feel more confident in the skills I'm asking you to demonstrate. I'll post the answers to this assessment exercise in the information section associated with this lecture. Don't peek. Struggle with it and take your best shot. Given a pump that displaces 0.5 cubic inches per revolution, being driven at 1,155 revolutions per minute, determine the flow rate in gallons per minute and cubic inches per minute. Given the dimensions of 4.5 inches cap diameter, 2 inches rod diameter, and 24-inch travel, determine the functional area of the cap end, the functional area of the rod end, the volume of the cap end at full extension, the volume of the rod end at full retraction, the time it takes to fully extend the cylinder, and the time it takes to fully retract this cylinder. Determine the force of extension if input pressure is 670 psi. Determine the force of retraction if input pressure is 670 psi. While you're at it, figure out what color this actuator is and what it tastes like. Take your time and do not rush this. The steps necessary to accurately calculate all these quantities are well within your reach. Remember, standard operating procedures dictate you use unrounded previous results for all intermediate calculations and only round the final results. That's it. In closing, remember that this content has been developed for edification only. While reasonable care has been exercised with respect to its accuracy, I assume no responsibility for errors, omissions, or suitability for any application or misapplication of its contents. Long story short, I'm going to dork up a calculation one of these days, and if I do, I'm going to do my best to rectify it by annotating it in the lecture with the correct solution. If you find my results off by a trivial amount, it's most likely due to a rounding error or my own laziness or sheer stupidity. In conclusion, this lecture presented a review of basic mathematics skills that are necessary for success in the hydraulics and electrical control of hydraulics playlist. We discussed common hydraulic units, algebraic manipulation at the unit level, unit conversion, circular area, annular area, cylindrical volume, and tubular volume calculations, differences between extension and retraction, and how the physical construction of the hydraulic cylinder affects output force and speed during extension and retraction, the relationship of volume, flow rate, and time, the relationship of displacement per revolution, rotational speed and flow rate, and the relationship of force, pressure, and area. I know some of these terms might be new, but the math should be well within your reach. If you feel incapable or unqualified to perform the math without outside guidance, I am urging you to seek help instantly or turn back now. Hydraulics uses the language of numbers, and you must have a basic fluency in this language to predict behavior, interpret observations, and understand the content of this series. Remember to review this material and practice these techniques as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.